What we're going to do here is calculate the Thevenin equivalent of the left-hand side of this circuit. So what that means is we're going to go ahead and try to represent all the junk on the left as a single power source in series with a single resistor, and calculate the voltage that would go across the load put between the nodes A and B. The easiest way to start this calculation is by knocking out our load, because it's what we're going to calculate eventually. So by taking it out of the circuit, we can then look at the resistance, or the Thevenin resistance, or the resistant R sub T, which is called the Thevenin resistance. And we start here with the 2K, and we add it with the two resistors that are in parallel, the 1K and the 3K. And to find their equivalent resistance, you put the product over the sum. Now what this eventually gives us is 11 over 4, which is exactly equivalent to 2.75. Sorry, that's kiloohms. I'm just going to say K because kiloohms is a lot on the tongue. So we take the 2.75 and call that our R Thevenin. Now we're going to take it with us when we go to calculate the voltage, Thevenin equivalent voltage as well. So the way you do that is very much in the same process, but instead of the perspective of starting at the A node and going left, we're going to start at the power source and calculate the loop there. But rather than talk about it, let's go ahead and show you. Okay, so we have our R Thevenin. To calculate the voltage, we have to start by changing colors and also using the correct tool. And you come around this loop here and we calculate I1, which is fairly simple because we can't consider the 2K because it's not part of the loop. So get rid of that guy, which gives us our 12 volts. And Ohm's law says that the voltage is equal to the product of the current times the resistance. So we have 12 volts over, because we're carrying over the resistance, which is just the two resistors in series, 4K ohms, which is going to give us 3 milliamps. Now, to calculate the voltage at this point, which because there's no current flowing is the same as at this point, which is what we want to know, we multiply the 3 mA by this 1K to calculate the voltage drop, which gives us 3 volts, and we subtract that from the 12 volts of the power source, which tells us our R Thevenin is equal to 9 volts, which is exactly what we were expecting with the tips from, or the hint from the question itself. So let's see. Let's get rid of the junk here and go ahead and satisfy the third part of this problem, which is asking what would the voltage drop across the 5K resistor be. So let's go back to our original . Go ahead and get this out of the way. So what this means is that now we can restate this expression over here, the single power source and the single resistor, the 9 volts, again using the right tool, 9 volts and the 2.75. But now, go ahead and insert our load, which is 5K. Sorry, I forgot my K up here. So we take the resistance again, and calculate the current. It's 7.75, let's see, off the top of my head, I think that's about 1.16 milliamps. I'm just kidding, that wasn't off the top of my head, I calculated that much earlier. So we then have the 1.16, we multiply it by the 2.75, which is going to give us a voltage drop of about 3.19. We subtract that quantity from the 9 volts that we originally had, and the difference is going to tell us what the voltage across the 5K resistor is. And of course I've forgotten to do this one in advance, so pardon me for half a second. It tells us that 5.81 volts is what we're going to go ahead and see at the load. So we have proven and verified the statements in the original question. The V Thevenin is 9 volts, the R Thevenin is 2.75, and that the voltage across the load is 5.8.